the opportunity to get to hear from a very, very, renowned personality in our field. I think I will not take time to introduce formally him, but I hope today there has been a little bit of conflict. I would have preferred to have many more people, particularly, other faculties, but I understand there has been a, superannuation ceremony going on. So some of our fellow colleagues are, stuck there. But we'll also request the students to convey this to your fellow students that they're missing something. So I hope you will understand that after attending today's session, that this is important to have a general, consensus view about the different fields across. It's not always necessary that you get bogged down by your curriculum or your research topic in your life. It's very important to have this diversity, and that is what we will attempt here, to get you exposure or flavor of different subject areas, way in science, arts, or culture. So with that, I can request Shonan to just introduce to the other people. Yeah.
Thank you, Professor. I'm Director IIST. Now I will invite Professor Umesh to introduce the speaker.
Good afternoon to all. It's a great privilege to introduce such a distinguished guest today. As scientists, we are very much used to confine ourselves to the boundaries of our subject or our specialities. Very rare occasions where people get opportunity to really bridge through a swath of technologies and sciences together to really bring great scientific value to the world. And when I look at the profile of Dr. Murthy Gudipati, I see that I wouldn't find a better example than this. Somebody who has research interests in physics and chemistry and IISs, planetary, interstellar, cometary, and atmospheric. He has extensively worked on exoplanet atmospheres, and he studies on ground a lot of radiation-induced damages in ICES, and very interesting tricks and methods they have developed for that. Fundamental atomic and molecular physics, VUV to far infrared spectroscopy and mass spectroscopy, and next generation space instrumentation and origin of life. So now you see the list is a abridged list, okay? And you can now imagine how many things are connected. And the person who actually started his journey in the city of Vijayawada in India, and he did his initial studies there. He did his master's in Hyderabad University, and then he did his PhD in chemistry in IISc Bangalore. After that, he moved to Germany, and he got a habitation fellowship there, very prestigious one. After that, in 2001, he shifted to NASA, JPL, where he has been performing as a multi-dimensional task, and in that he has been a very active participant in the Europa Clipper mission, Rosetta mission, and very interestingly, which actually does not sound very complicated, but if you really get into the deliberations, you will realize is a sample return mission from a comet. I mean, it's something might sound very simple because humans have done sample return from other places, but comet is something really very hard. And I am really surprised that some work on that has been done. So he has been part of NASA since then and has done exemplary work in that field. I can go on. There's a very long list of accolades and work here which he has done, but I'll not take your time. I would invite Dr. Murthy to give his seminar. Thank you.
Thank you, Umesh, and thank you, Dipankar. It has, let's see, this is off. Okay, this is off. Okay, good. This has been a long coming because I told myself once Europa Clipper is safe, I will take a sabbatical. So the safest place for any spacecraft is up in the space. So we achieved it. I talked about Europa Clipper 2 days ago, and I would not talk about it today. Today, the focus is why we want to look at organics in space. Is there an issue? Okay. So organics are very much connected to life, as we know of. And that is one of the main motivations why we want to see and follow organic matter in the space. Okay. What I try to do is to connect how space missions can give us, such as JWST and such as Rosetta, which went to a comet and followed it almost from -3 AU to +3 AU. And what is that we learned, and what is that we still have that we want to understand in the future? Okay, that is the reason. Yeah. Oh, I see. Okay. Huh? Rejoin. Okay. So probably it went down. Okay, that's good. Rejoin. Okay. Control C. And that one. It is there. They are here. Users are here. And share. Okay, good. Okay, good. Wow. It was not sharing. Okay. Is it sharing now? Oh, yeah, it's sharing now. Do they have it? Okay. Is it there? Okay, good. So that is what I want to do today. But before going into, I also want to, bring one thing very much to the attention of everyone here, especially those who spend their time on implementing technology. So we need technology to do science, and we need science to lead to innovative technologies. Without science, technologies can only go so far. And without technology, science cannot make progress. So it is like body and mind that have to work together to have space explorations where you can ask bigger questions and try to answer those questions that are otherwise thought to be impossible. And also, there are 4 different corners. Sorry, it is rotating. I should not have made it rotating, but it's okay. There are 4 different aspects of any space exploration. One is the observations. So what you do is you put something together, thinking what you know, what you want to see, and then you do the observations, whether it is ground-based or space-based. And once you have the observations, you build some theoretical models based on your present-day understanding. And typically, observations and models don't go well together. There is a problem. And when you have the problem, then you go to the experimentalists and ask, hey, I have this problem. Can you simulate that in your lab and then give us data that can probably be used? And those experimentalists then go and then do all the stuff and then work with the modelers, try to understand the observations better, and then they realize that, oh, the pointing was not correct. The resolution is not good. So we have to improve our resolution. Then they go to the engineers and technologists and say, can you build us better, bigger, wider, more sensitive, equipment? Okay. And that's how all these 4 things together work in iterative fashion, constantly improving our understanding of the universe. Okay, without any one of these things, the other part is essentially useless. Okay, so these are the two important things that I want you to keep in mind when you do something. Think about the big picture and see that you need both science and technology to go well together. You need all the 4 branches of space exploration that have to work hand in hand together. Okay, so I wanted to take that time to talk about it. Now, let us see. The biggest question we all ask, in fact, that's what the question that led me to work towards NASA. Not necessarily that I knew well that I would be going to NASA, but I never thought I would go to NASA. But I was always interested in asking questions. What is happening around us? Where are we from? How did life start here? What are all those things up there? And can we understand if this kind of conscious life could exist somewhere else? Okay, these are the most fundamental questions all of us have. Whether we do science or not, these questions are always there. And that is the question, the same questions actually drove me also towards science. And in order to understand, is there life elsewhere, we want to try to follow what we know of life like what we have on Earth. And life on Earth needs these 4 ingredients. And there is a stability that you need. There's protection from radiation, vacuum, temperature, and all those things that you need. So of those 4 things, we followed water yesterday, or day before yesterday, and we went to Europa. Okay, I will not talk about it now. So we'll follow organics today and see where are these organics. This is not about organics, but this is about our universe, how the JWST telescope has shown us such a beautiful thing, and it is a conglomeration of several hundreds of galaxies probably in this frame. And each galaxy, like our own Milky Way, has billions of stars, and between the stars, what we call as interstellar medium or interstellar space. And that interstellar space is what is the important place where we want to look for when we want to follow organics. Okay, and this interstellar medium is essentially, when you zoom on any one of these galaxies very much, and the space between 2 stars would be the interstellar medium. And some of these parts of the interstellar medium are pretty cold. Probably I will show in the next slide. And in those cold regions, you have predominantly water and these simple molecules like carbon monoxide, methane, ammonia, and methanol, something like that, very, very primitive molecules, are frozen into ice grains. Okay, these regions we call as dense molecular clouds. And that is the starting point of organic matter. Okay, and in other words, this is what is interstellar medium. And if you see the temperature here, some of them are pretty hot. And as you come down here, you see that 50 Kelvin to 100 Kelvin and 10 to 50 Kelvin. And also you have very cold, giant molecular clouds here. But look at the number density here. Even the highest number density here is vacuum on Earth. Extremely high vacuum, ultra high vacuum on Earth. That's what I gave here. This is what is the number of molecules or species per cubic centimeter on Earth. And that is 10 to 7 maximum. So 10 to 12 times lower than what we have here. Okay. So number density is extremely low. But to compensate that, the area or the volume of it is enormous. So we still have a lot of material out there. Okay, we will be focusing on this dense molecular clouds, are also called dark molecular clouds there. Okay. Now, I told you that ice and volatiles are frozen, and in these molecular clouds, and this is another beautiful, observation from JWST again. Previously, other telescopes like Spitzer have given data, similar data, or ISO from ESA, Infrared Space Observatory. This is about the condensed matter, that is the condensed ice grains in the molecular clouds. This is such a beautiful, extremely high resolution spectrum here, going from about probably two microns all the way to 14, 15 microns. What you see here are the molecules that are the composition of these ice grains. Okay, you have water here. It is 99% in amorphous water ice form. I would not go into detail today because of lack of time about this. We have been working on that. But you see very beautiful CO2 and CO bands here. And even with JWST, you could have even see the natural isotopic 13 CO2 and 13 CO bands. This is the first time ever that kind of sensitivity has been achieved. Okay, and not only these two, we have methanol, we have ammonia, we can see the methane, silicates, and all these are simple molecules, right? Water, CO2, CO. CO is one of the most abundant molecules after H2 in the universe. Okay. So these are the molecules that are probably everywhere, and in these cold regions, they condense to form these ice grains, most likely on a silicate grain, okay, because that is a nucleation center. Silicate grains are probably generated during supernovae and spread over. And then again, this is the ice phase. Okay, in the gas phase, we have seen a lot of molecules, and most of them, not only organic but also non-organic molecules or inorganic molecules. But here, the gas phase spectroscopy is inherently biased towards molecules with huge dipole moments, because the microwave spectroscopy is in emission and sometimes also absorption, but mostly in emission spectroscopy. And what happens is you need an enormous amount of dipole to get these emissions strong enough. And that's why you see that most of the molecules have CN or some other groups on the end, making this long and longer the molecule, higher is the dipole as well. So the organic molecules detected here in the gas phase, one of the questions that we still do not understand is, are these molecules made in the gas phase through the gas phase, molecule-molecule collisions? But think about the density. The density, number density in this space are so small. How many years are probably hundreds of years will take for molecules to form higher molecular species? Do they form in the gas phase, or does it form gas molecules accreting onto these grains, or does it happen in the bulk as ice? So these are the three things that we have to still investigate and understand how the molecular evolution happens in and around protoplanetary disks and in interstellar medium. Okay. In addition to these molecules, we have a third class of molecules. It's called the PAH, polycyclic aromatic hydrocarbons. These molecules are aromatic molecules that are very robust. In fact, they are in the combustion exhaust of our cars. They are so stable that typically in the gas phase, they can be at any temperature, nothing happens to them typically. But we know that once we put it in ice, they are destroyed. Okay, I may not go into detail on that either. So these Interestingly, the emission from Orion Nebula, this was, I think, again, IISc data. These are the emission lines that were observed, and when they made a polycyclic aromatic hydrocarbon mixture of the several sizes, they could actually match these emission lines very well, and that's how the PAH hypothesis started. Okay, so long chain, high dipole molecules, PAH molecules, because these PAH molecules have strong dipoles in the emission and in the vibrational modes, and also in the electronic states. So they're much more visible to us. Okay, and then in the ice we have simple molecules. Okay, these are the three different phases, and these are the ones which we start with. In our solar system, let's just go through quickly what could have happened. We have this dense molecular clouds, and there would be a collapse because of external or internal, gravitational collapse, or supernova, whatever it is, causing these clouds to come together, and then the pressure and temperature are so high that it starts forming nuclear fusion. So that's what we call as lighting up of a star. That's when it starts burning, and that's when it starts accreting also material. So that's what happens probably about 50 million years plus minus whatever it is, and then you start forming the initial debris disk. It becomes even bigger. It becomes the disk form. You have jets of radiation going in the vertical direction. It's amazing that we could actually see a photograph of or image of that kind of jets recently with JWST and other telescopes. But then at one point, all the debris are cleared, and then we form a solar system that is more or less like what we have today. Okay. Now, question is, where are all these organic molecules here? What happened to them in their entire journey to this point? Okay, and that's the reason why we need to follow this pathway and see how the molecules can evolve, ultimately come to Earth and then start life on Earth. Okay, this is how we construct our questions. This is the science thinking that we have to justify when we want to do an observation and justify why we need bigger telescopes like JWST. So what are these protoplanetary disks? So we went from interstellar molecular clouds and came to the protoplanetary disks here, and these are this accretion disk it is, and these are the jets coming out. You see the temperature here, and you see the ice region, which means that water will not evaporate. It will stay in the form of water ice grains. And you see the small, pebbles and planets forming here. This is where the planets form, okay? And you see these kind of things now JWST has. And ALMA and JWST have started looking into these kind of things. These are the ALMA data, actually. So many forming things. Okay, I'll try to show a simulation where you can understand how this is happening. And keep one thing in mind. It's all just forming these planets, and then we have everything cleared, would have been perfectly fine. And probably we would not have existed if that were to be the case. There was something else happened. And that's what we'll see what happened there.
In the past few decades, our spacecraft have visited many exotic locations in the solar system, including icy comets that have orbited the sun since the planets were still taking shape. We have explored relatively tiny asteroids, ancient rubble piles held together by weak gravity. And we have found that the largest asteroids resemble the building blocks of planets themselves, all of which suggests that these objects offer clues to how the planets formed. And we have even found evidence for a violent rearrangement of the planets. Computer simulations allow us to reconstruct the formation of our solar system 4.6 billion years ago. We use the laws of physics to create these virtual experiments in order to figure out how planets took shape. After the sun ignited, most of the material around it had flattened into a disk of gas and dust. We can zoom into a simulation of a portion of a thin disk, a small piece of the universe in a box. Here, a dense swarm of objects clump together to form what astronomers call planetesimals. This simulation addresses how planetesimals form from much, much smaller particles, the size of pebbles. Pulled together by gravity, some planetesimals formed the planets, while others became asteroids and comets and dwarf planets. As the planets accreted, they carved out gaps in the disk. But the solar system remained quite cluttered. If we look at the orbits of the planets and accelerate the passage of time, so 1 million years pass by every 10 seconds, we can watch how the debris cleared. In this simulation, the giant planets, Jupiter, Saturn, Uranus, and Neptune, shift their orbits, and many unlucky asteroids and comets and dwarf planets get kicked out of the solar system. The migrating giants wreak gravitational havoc. The distribution starts out quite flat, but as most small objects get tossed out, others settle into stable orbits that allow them to coexist safely with the planets.
So that is the most important thing that in our solar system formation, we had Jupiter, Saturn, Uranus, and Neptune not in their stable orbits as they are now. And that was when there were so many debris, that means comet-sized bodies were still in the disk. And so when these gravitational instability caused these bodies to be scattered everywhere, they were also scattered onto the Earth and bombarded Earth and also Moon. And that's why we have craters on the Moon that are dated as early as 4 billion years. And then we think that these bodies brought water and organics onto Earth. And that could have immediately, soon after, led to the origin of life. Imagine that if there were to be planets found happily adjusted in their own orbit without any gravitational back and forth, we would not have had those water and organics on Earth. We would have had probably the accreted material, but there was another thing that happened to Earth before this had happened. That was a violent collision between two, probably half size of the Earth's bodies. That led to the Earth-Moon formation. In that very violent collision, everything got heated up, and most likely Earth would not have been habitable with material that was needed. So this is what I told you is put in a nice clock here. This is the 4.6 billion years ago when the solar system formed. Soon after, we have Earth-Moon formation, and between about 4.1 or 2 billion years and 3.8 or 9 billion years, this is where the giant planet instability led to so-called the late heavy bombardment. Imagine soon after the first bacteria were dated on Earth. So that was the reason why we think that that kind of bombardment, that kind of instability, and the entire comets and asteroids falling on Earth was the triggering point for life to start. So this part will be repeated tomorrow also, but in a much more quick fashion. Okay. Now let us connect the interstellar ice grains, which became comets, and how they are made of. This is again the composition of ice grains that I showed you from JWST. Just put it as the ratio with respect to water. And this is just a mirror image. It's not negative or positive mirror image here. But if you see and compare with comet outgassing, comet outgassing has a lot more molecules here. But major components are so fantastically mirror imageable. Okay? This clearly shows that the interstellar ice grains we were talking about that were seen by JWST, indeed, during the protoplanetary disk formation, formed from the micron-sized grains to centimeter-sized pebbles to meters and kilometer-sized bodies. Some of those bodies became planets and moons, and some of those bodies did not grow so big. And those are the ones which actually were scattered. Okay, so you see the compositional similarity between these two bodies here. Okay, that is what I show you here in this. These are the interstellar ice grains, which we have pictorially represented because we have not yet sample written from there. It's very difficult to do it. And these are actually the molecular clouds. This is very well known Horsehead Nebula, and there are so many stars here being born almost every time. And these are the grains that are in these molecular clouds, which in protoplanetary disk lead to this loosely bound, irregularly shaped comets. Okay, and we have seen previously that the composition in a volatile composition is very similar here. Okay, such a compelling analogy here. And you have also seen that these small bodies were scattered everywhere around. And in fact, what our solar system looks at is not a disk like this, where we have the inner solar system, outer solar system, and Pluto and whatnot, and then Kuiper Belt objects in one disk. But actually, it looks like a sphere with all these arc cloud bodies that are almost 400,000 AU wide. Okay, our solar system is like a tennis ball, not like a frisbee disk. Okay, so these are the comets. Okay, and what happens to those comets when they come closer? We see this spectacular display of outgassing, which we call it as coma, and they actually can span to millions of kilometers in the sky. And these are the outgassings that the Rosetta mission went, and also you can do ground-based spectroscopy to understand what kind of molecules are there. Now, we have also done laboratory work to understand what happens. You have seen this just a few slides before. What we did was we took these most prominent ingredients and put them together into ice. For example, ammonia, methanol, carbon monoxide, carbon dioxide, methane, and water in any form you want. That nitrogen, oxygen, carbon, hydrogen. Nitrogen, oxygen, carbon, hydrogen containing molecules. You put them together, and then you make them ice grains, and then subject them to the radiation, warm them up. In the laboratory, it was found that there were amino acids made. Okay, there were molecules that form micellar walls here. These cell wall type molecules are critical for every living cell on Earth. Okay, these are the molecules that could be formed from this simple combination that existed in the interstellar ice grains. Okay, now we start understanding. Interesting thing is, radiation gives and radiation takes. It gives life and it takes life. Okay, in a sense, if you put too much of radiation, you damage everything, and it will go back to more destroyed And with enough radiation, you can actually make these kind of molecules. So this is what we have found in the lab. And in fact, if you add something else to that, you also start making nuclear bases that are needed for DNA. You can make amino acids that are needed for proteins, cell walls that I have shown you here. So this is what I think could be happening in the interstellar ice grains by lab work now. You see how important is lab work. We have observations, and the lab work took it beyond the observations. We have observations that we have water, ammonia, methanol, and carbon dioxide and carbon monoxide. Lab took it and went and looked at it and said, we have much more happening there. It could be giving us more complex molecules. That's how lab helps observations and even drives the observations. That's what going to be my conclusion later. Now, one of the questions is, if you saw in the previous slide, these molecules, the bigger molecules, were seen only when ice was irradiated and took to the room temperature. And then they did conventional chemical analysis, wet chemistry, if you are aware of it. But that doesn't represent the interstellar ice grains, which were at 10 Kelvin. So we had to address this question. What kind of complex molecules could have been formed in that 10 Kelvin interstellar ice grain? How do we analyze it? Spectroscopically, we have been having a lot of problems because water ice in the infrared absorbs so strong that anything that is smaller than 1%, you cannot see it anymore. And that's the reason why JWST spectrum, the most prominent features are water ice and then carbon dioxide and carbon monoxide, which are extremely sharp absorption bands. And you know that the area under a band is what is the number density of the molecules. If the bands are sharper, they could be longer for the same concentration. If the bands are broader, then you get into actually the noise floor. Okay, so we were limited. So this is again, we were pushed to a wall. And that's the time when I decided that, okay, we have to think beyond that. What we did was we took infrared lasers, a pulsed infrared laser, and we would shine it, focus it on the ice of all kinds of radiation processing. This pulsed infrared laser is tuned to the OH vibrations of water. And what does it do? In the 5 nanoseconds time, you expand the OH vibrations or the OH water molecules in the laser path in such a way that you generate a shock wave. And that shock wave moves backward and forward. And as it does, it actually takes this water into the gas phase. You're essentially pulling water ice, a part of it, out of the ice into the gas phase. Once we get it in the gas phase, we cross that gas phase with a UV laser, which does RAMP, resonance enhanced multiphotonionization. Once you ionize the molecules in the gas phase, the playing is easy. You put electrostatic plates, and then you pull them, and then you focus them, and then let them float. That's what is called a time-of-flight mass spectrometry. We get everything. So what we saw with simple mix of oxygen, nitrogen, hydrogen, and carbon, that is, this is, for example, methanol or ammonia, we could see molecules that were important for building blocks of life. And that's what was observed by Rosetta. In fact, these are the molecules we found. You see HCN, formamide, estamide, acetone, something is there, acetone and all those things. Hydrogen is here, and the methyl isocyanate. You see, almost all these molecules have been found in comets outgassing. In addition, they've also found glycine, okay, and higher molecules. That is now our aim, actually, to extend this one to see whether we can also see in the interstellar ice grains at 10 Kelvin, can we see also these complex molecules? Okay. Or is it limited for only warmer temperatures? Okay. Let us quickly have a look at the Rosetta mission now. The Rosetta mission was put in place because they wanted to understand and investigate what is a comet made of. Does it have the primordial composition that we talked about in the interstellar ice grains, put together and formed this and then preserved it for 4.6 plus billion years? Or has it been completely processed and then it has no more memory of the past? This was a very ambitious mission, and these are the parameters for the spacecraft. If you want to look into 850 watts at 3.4 AU, and solar panels are 64 meters square, and for Europa Clipper mission, solar panels are 100 square meters. Okay, so yesterday we talked about it. And the comet, it has a shorter period comet, so it is called a Jupiter family comet, where it is trapped between Jupiter and Sun. It comes as close to the Sun to 1 AU and then goes back to Jupiter probably 5.5 AU or something like that. Or yeah. So that is the orbit. Here you see that 5.7. Not bad. Okay, a couple of things. And at the perihelion, it is 38 kilometers per second. Okay, that's the thing. Look at the density here, 0.5 grams per cubic centimeter. That shows we have silicate grains in this. That means there are part of dense material which is 3 plus grams per cubic centimeter, and the rest of it, if you put together, it shows that a comet is 70% porous. And that also actually agrees with these small grains coming together because there is no gravity. And they are just stuck together in almost no gravity environment into this loosely bound comet. Once the size becomes big, then the gravity becomes higher, and then you start fractionating these grains into bigger and bigger, our Earth-like or Jupiter-like systems. Okay. Let's see what we have. Okay. So the data that was taken was by Rosetta. Rosetta is a time-of-flight instrument on that, and it was launched in 2004. Philae is actually piggybacking on that. This was the first ever human-made spacecraft landing on a comet, and the end of mission is 2016. And this is Katrin Altweg, my colleague from University of Bern. She was the PI on this Rosetta instrument, and they, as I said, they found all these molecules that we also found in the lab, as well as they found oxygen. That was very surprising thing there, and amino acid glycine was found, and they gave some nice names for that, but that's not the main important thing. We have also seen signs for non-volatile organics on the surface of the comet, but you see, this is what is the resolution you get. It's an accumulation of all the organics, so you don't know what those organics are. Are those organics polymers that we need for life, or just like tar? We don't know. That is one of the reasons why people wanted to go and get surface samples to understand. So this is a summary of Europa Clipper mission. Rosetta mission.
Once upon a time, a spacecraft named Rosetta was launched into the night sky. A long, long journey lay ahead of her to uncover the mysteries of our solar system. Rosetta carried a little passenger, the lander Philae. Rosetta's exciting mission was to follow the comet as it traveled around the sun. She would learn all about the comet and how it changes as it gets warmer and warmer, while Philae would visit the surface.
10 years of travel.
But as she got closer, Rosetta realized that the comet was much more complex than people had first thought using telescopes from far away. It almost looked like two comets stuck together, and from some angles its shape was really rather strange. It was the beginning of August, and Rosetta had to maneuver several times to get closer and closer to the comet. The nearer Rosetta got to the strange world, the more wonders she discovered on its surface. There were craters, cliffs, and boulders the size of houses. Rosetta spent many weeks studying the surface of the comet, sending lots of information back to Earth. Rosetta had to plan the exact route around the comet to make sure that Philae would land in the right place. Soon it was time for Philae to make the final preparations for his great adventure. He checked that he had everything he needed to land on the comet. Finally, the moment everyone had been waiting for arrived. As the world held its breath on the 12th of November 2014, Rosetta moved into the exact position needed to make sure Philae would reach the landing site. Philae was away. It would take 7 hours to reach the surface,
So it would take
and the
7
moment
hours.
he had been dreaming of
And the
had
landing
finally
on
arrived.
less than 10
He had
kilometers.
reached the surface
Now
of the
engineers here
comet.
can think about how
But all
precisely
was
that-
not right. His harpoons did not fire.
that was the
Philae
problem.
realized he couldn't relax yet. He was rising from the surface again. Philae was scared he might drift off the comet completely. This was not in the plan. But eventually, he came back down again.
But that was a dark spot. There was no sun there.
However, as he looked around, he realized he had landed in a completely unexpected location. Philae immediately set to work on studying his new home. It took him just over 2 days to conduct all the experiments he had brought with him. After all his hard work, Philae began to feel tired, so he made sure
battery
to
was
send
dead.
all the data he had collected
Philae
back to
could not do
Rosetta.
anything. That was
As the sun set over Philae's new home, he fell into a deep sleep. One of the most important questions scientists back home wanted to answer was where Earth's water came from. Could it have come from comets and asteroids billions of years ago? Rosetta was surprised to discover that the water vapor flowing away from her comet had a different flavor to Earth's oceans. The scientists wondered what it would mean for their theories of how the solar system evolved.
actually more recent what says.
There
it's
were many
very
other
similar.
types of gases too, and it smelled like a weird mixture of rotten eggs, horse stables, and marzipan. Rosetta also collected thousands and thousands of dust grains, small and large. Some of them seemed very fluffy, like the head of a dandelion. As the days and weeks passed, the comet looked more and more spectacular. Besides water, Rosetta found many other molecules as she studied the atmosphere of the comet, including lots of oxygen. Scientists were very surprised to find so much. They thought that most of the oxygen would have reacted with other atoms, but perhaps it had been locked into the ice when the comet formed 4.6 billion years ago. The scientists were excited by what this discovery could tell them about the history of the solar system. Scientists also came to understand that comets were made of the dusty and icy material left over after the planets were formed, and so they contained some of the oldest and best preserved material from the birth of our solar system. Rosetta had made even more remarkable discoveries. She found ingredients that were crucial for the origin of life on Earth. Perhaps comets had helped seed the Earth with these important ingredients when our planet was still very young. Finally, after 786 days of the comet, the last day of her extraordinary adventure arrived. On the 30th of September, 2016, Rosetta started her descent to the surface of the comet.
So this is almost 10 years since the mission ended. Even now they analyze the data and they get science out of it. And the most recent one is, in fact, if you put all the D2H ratios of entire water that is on Rosetta, on the comet, it actually corresponds to what we have on Earth. So this is a debate that have been going on. Is the water on Earth from comets or not? So now I want to tell you what these missions that have big questions are about. They are not about you as an individual wanting to achieve great things or have a pride or have your ego satisfied. These missions typically last 3 generations, if not 4. The senior people will start putting a mission concept together along with the junior colleagues and students, and it takes decades sometimes before the mission gets approved and launched. The first mission concept was 1985, and it was launched how many, 20 years later, okay? By then, the senior folks around who wrote that would have retired or died, okay? And then there would be the new generation coming in while the mid-career scientists and engineers carry on to be the seniors. We have new generation coming in. So this mission in its lifetime has generations carrying on and new generation being trained. And that new generation at the end of the mission not only uses the data to thoroughly understand what this whole mission is about, but also comes up with future missions that can achieve even better, ask much bigger questions. And that becomes an emotional thing for those people who have worked for decades on these missions. And
whenever I look at a comet in the sky, I'll always think about this final moment in the lifetime.
This is the human part of space missions.
It was truly a trip to the unknown.
It's a bittersweet moment, to tell the truth.
And you also see that we have
in that
diversity
death of the spacecraft.
from everywhere in the world.
Sadness
That's
in
also an important
something that's been a key part of our lives for 25 years. Some of the things that happen in the course of a mission this long is there are people who have passed away. On the other side, there are the babies who've been born.
As time passes, things change, people change.
It's sad, but it has to come to an end at some point.
It's kind of like every mission has to have death because then it leads to birth of other missions. It's kind of like evolution.
We have acquired a ton of scientific data. There will be analysis for decades.
It's immortality. Data it will be there forever.
I'm not going to say farewell. I'm going to say thank you.
I don't get a sad feeling. I am just excited that we, humankind, know so much more about the universe now, thanks to Rosetta.
But it is leaving us still with a lot of questions.
There are a lot of questions still to be answered. Goodbye, Rosetta.
Goodbye, Rosetta. Thank you so much. Bye, Rosetta.
Au revoir. Auf Wiedersehen.
Bye, Rosetta.
Goodbye.
Rosetta, great job. You did it. See you around, buddy.
Sleep well. Good night.
Goodbye, and thank you so much.
Bye-bye, Rosetta.
Bye, Rosetta.
Thank you, Rosetta, for your dedication to learning the unknown.
Rosetta, thank you.
Rosetta, we are going to be with you all the way in your final journey.
It's been a wonderful, exciting ride.
So that's how it is when you work for decades in a space mission. So put it together, our lab data and more importantly Rosetta spacecraft data indicate that the molecules that are organic molecules, especially that are required to build molecules of life, are potentially are still being made in these interstellar molecular clouds, ice grains, and could form the core of comets unaltered and probably delivered to Earth 4 billion years ago because of the gravitational instability of bigger planets that were formed. That could have started the life on Earth. So we know that these kind of smaller molecules have how they could be made now, thanks to all these decades of work. We know that these molecules are there. We know that they could be delivered, but we still do not know how the larger, more complex organic molecules are made, because we still have the lab analysis, except at room temperature, in the interstellar ice grains, or what we detected from the rotational spectra of gas phase molecules, we have limited understanding. What is the molecular inventory that can be really large is something that is still missing. Okay, and present capabilities of lab and instruments cannot cater to that. So we need to come up with new instruments, new sensitivities, and new lab work. And this is what I told you, exactly in the second slide, all the four corners. We are stuck now. Now we have to, in order to understand where these larger molecules are formed, we need to come up with new hardware, lab, and space missions. Okay. So we need to think out of the box, and I think some of us started really thinking in these directions. How can we break the barrier of microwave spectroscopy that is limited by high symmetry and large dipole moment? What happens if you have low symmetry and the bigger molecules? What are the things that you have to combine observations with lab work? And these are the things that we are actually started working. And that's why the future is in large molecular astrophysics, I think, and planetary sciences. So the one thing that I have been always advocating is to get a deeper drilled comets core sample in cryogenic conditions. If we get it, let's say about 25 Kelvin or 20 Kelvin or less, okay, frozen, and then bring it back to Earth, then we can actually analyze those samples and see whether indeed these large molecules are made there or not. And we have done this drill as a Keck Institute of Space Studies program several years ago, probably even a decade ago. I don't remember it anymore. But we have been stuck with the re-entry problem. We could not get such a low temperature system, and that's why they have compromised and then warmer surface sample return, and there are people working on that. For me, if it is only a linear progress made, I'm not so much interested, because okay, we will get those samples, we may see some macromolecules, but we have to really get the cryogenic samples. So we have to wait for the next generation cryogenic sample return, and also it's extremely expensive right now. So we need to learn more about how the gas evolves in this interstellar medium versus the condensed matter, because gas phase chemistry or gas phase evolution of molecules may have only so much of possibilities, whereas in the condensed phase you have much higher densities of these systems. So we need to actually see which is better, and all those things, for which we need laboratory work also. A main goal should be to actually understand how we can identify, detect, detect, identify, and confirm larger molecules. That's what I think is the future. Okay. So that's all for now. I think Rosetta made so many groundbreaking discoveries, including being the first spacecraft to send a lander on a comet, and it had a partial success, and also it has shown that the organic inventory, including phosphorus and sulfur, are already there in comets. And by extrapolation, by looking at its porosity and density and all those things, we take the comets to be preserving the pristine material that was coming from interstellar space. That is interstellar ice grains. So that is the journey of an interstellar ice grain towards and to give life on Earth. Thank you.
Yeah. If there are questions, you can have them now. Why the orbits are only in a plane?
Which one? In our solar system. Can you give him that one? That's probably is better.
So why are the planets which are like the orbits around the sun, they seem like they're in a plane?
Yes.
And in general, the Milky Way galaxy also is represented as if it's in a plane. Like
Yes.
not exactly plane, but
Yeah.
it's not a three-dimensional to per se. So
what happens is when the molecular clouds in 3 dimensions come together, and in the middle, the density becomes so high to ignite, forming the nuclear fusion chemistry reactions. At that time, what happens is the momentum of material being pulled together with gravity inside has to be conserved, and for that reason, the molecular cloud starts rotating, and there is a momentum of gas going upwards. It's almost like it starts rotating in that axis, in one axis, where the energy is flowing outwards, plasma is flowing outwards, and the matter is actually rotating. So when this kind of rotation happens, all the material gets pulled into the disk. It's like, you know, if you look at making pottery, it is very similar thing. You have a spherical thing, put on something and start rotating, it becomes flat. And that's because of the conservation of angular momentum. And that's why I think any solar system that we have seen so far, including that ALMA, images of protoplanetary disks at various stages, they're all flat, more or less flat.
So my question was, for the Rosetta mission, you said it would take 30 to 40 years for the whole mission to go up. So like they would have had to guess when the comet would be closest to Earth, so that would be the perfect time to send the missions. Like, yes. Did they imagine already like exactly how much time it would take for the mission to launch?
That's a very good question. That is exactly why they chose this particular comet. It is called Churyumov-Gerasimenko. These are the two people who actually discovered that comet. And this is a short period comet. That means it has an orbit period of 6.2 years or something like that. So they know exactly when the comet would come, where the comet would be at what time. So they have sent the spacecraft well in advance to travel 3 astronomical units away beyond the asteroid belt. It took 10 years for them, for the spacecraft to go there. And from that point, it started actually following the comet all the way through the perihelion and post-perihelion all the way through the 3 period. And so that's the reason why it was a long mission. But in that period, the same comet would have done 2 or 3 rounds around Sun already. So that's no problem because they know when it was coming there. That's it. The other comets that come from Oort cloud, you see I have shown this ball, and that Oort cloud comets come once in a while when there is this, gravitational instability, and those come once in a few hundred years. Okay, and those are difficult to follow. Their trajectory is actually through the disk, vertically coming through the disk. In fact, there is one coming like that. In 2030-ish, it will be, the perihelion would be close to Saturn, 10 astronomical units away. But it is the biggest comet ever we see. It's about 100 to 200 kilometers in diameter. All the comets we have seen so far are about 10 kilometers or less, plus minus. This would stay, that means we would be able to see the comet for almost 10 years.
I had one more question. We know that the comets are like relatively much smaller, so their gravity is really small. So you showed in the animation that the orbit around it was like a triangle shape. So like, what is there something special about that shape, or how did they manage to keep it orbiting that comet?
Very good. So that's why I told, I have shown in one of those slides the parameters of the comet. At the perihelion, it was going at 38 kilometers per second. Okay, Rosetta spacecraft, the biggest payload on the Rosetta spacecraft was the fuel. Okay, because it doesn't have gravity, you cannot actually have a gravity used, orbiting. So everything that the Rosetta has to do, it has to keep up the velocity. It has to get faster and faster as it comes closer in order to be next to that, so that to have the almost zero differential velocity. And then it has to go around in that speed around the comet so that it can get a tomography of it. It had a radar on the spacecraft, and an antenna on the Philae. And so when Philae landed, they could actually see through the comet what kind of heterogeneity that comet had. So yeah, it was a lot of gas, a lot of fuel. Yes, yeah. Good question.
Any other question?
Thank you for the wonderful talk. Just one clarification, like many of the experimental work, whatever you have shown is from the small molecule, like linear amino acids, etc. are forming. But are there any experimental work which shows that formation of nuclear bases like
yes.
adenine, thymine?
Yes, yes. I have shown that in this actually. For that we need to add pyrimidine. See there?
Yeah, but not from the small molecules like methane. Sorry.
We have not been able to just get from this mixture. From this mixture, we were not able to see them. Maybe their production is not enough, but so far, as I understand, when you put pyrimidine into ice, then you make all the nuclear bases. Maybe we need to understand how to make pyrimidine with the starting materials.
Yeah, and one of the experiments showed the methanol water and the ammonia water.
Yeah.
In that, some peaks are there nearby 100 mass unit. Is it a clustering? Is it from?
Yes, yes. We also have water clusters.
Oh, is it water clusters?
Yeah. Whenever you have polar molecules, you also get water clusters. See, this is what we wrote here, high clustering. I have avoided showing you other experimental work because I didn't want to bore everyone with intricate physics and chemistry of ice. Okay. I have those things. If you want, we can discuss about that.
Okay. There are other questions?
In the same sort of medium, it would again probably be carbon-based, water, and so on. Is that so? I mean, it won't be very different from what life is on Earth.
Yeah. So the problem is, this is a very unconstrained issue. We know so far only one form of life in this universe. We have zero proof that there is any other form of life anywhere else in the universe. We have been searching. We are doing right now in our planetary systems, thoroughly searching Mars and every other place, including Europe and all. If we find any other form of life that is similar to what we have here, starting with carbon-based in the water medium, then we think that it is, by extrapolation, in our solar system, this is the most common thing. Beyond our solar system, I'm not sure whether, because the nucleosynthesis in a star is very similar, I'm not convinced that there could be other forms of life, because all the nuclei, if you look into nucleosynthesis, have certain abundances there, okay? And that is irrespective of what kind of star it is. So these kind of elemental abundances is one thing that is determined. It is a deterministic thing. Second deterministic thing is, if you look into water, it is one of the best solvent. If you ask what are the most fundamental requirements for life, that is gradients. You need to have electrical gradient for information transport, and you need to have rigidity. At the same time, it has to be flexible, so that you can have catalytic reactions in biomolecular systems. All these things, the flexibility plus rigidity is provided by carbon-based macromolecules and water-based solvents. And that's one of the reasons why I think it would be more difficult for me to think that life could be there anywhere else with other form of building blocks other than carbon, nitrogen, hydrogen, oxygen, and phosphorus, whatever it is. So that's, on the other side, I don't want to push that too hard, because I am biased by only one example in the universe. So if I'm biased with one example, I don't know any other examples, my mind is not open. So this is where the dilemma comes, and then we should be more pragmatic and more open-minded and say, maybe there could be life of other forms, but it is unconstrained. We cannot go and look for everything everywhere all the time. So we look for only the thing that we know is definitely exists. Did I answer your question? No? If not, you can ask me again. Okay.
I just have a short question. It's a pity that the lander landed in a shadow region, but what was originally planned for the lander? If it had been in the
if it were to be landing where it would land, it would have been awake for a longer time. If the harpoons were to fire, it would have actually anchored itself, and having solar panels charge its battery was the most important thing. So they could have done more radar observations all around the comet, gotten more homogeneity or heterogeneity of that, and probably it would have analyzed more samples on the surface, but it would not be mobile. It would stay there and then analyze more samples. It's not a rover or a hopper. Yeah, it hopped it unintentionally.
Thank you.
Yeah, you're welcome.
Okay. Do we have more questions? Anywhere? Online? Anything?
So what are the next plans?
Next plans for comets is the cryogenic comet sample return.
But you said it is hard
It's
because
very,
of the
it's very
temperature.
hard. Yeah, we should work on. People like me who doesn't have to show papers can work on it.
But is there something in the pipeline?
Yeah, we have been looking into it. At least we need to mature the concept and all those things. But now there was a discovery mission proposed, but not funded, along with this Venus missions, was a catch and go comet sample return from the surface. Maybe that would be the more possible next mission to get the surface sample. But we need to actually, the next step for us to follow, the organics in whatever it is in our astrophysical environments and including on the Earth is, we need to just break our conventional wisdom and go out of our comfort zone to understand how can we identify extremely complex molecules in space. Maybe there may be a few of them in the gas phase. Definitely there will be more in the ice grains and other things in the protoplanetary environment. How can we identify them? Because we cannot, answer cannot be we cannot. That's the only way we can do it.
Yeah, the comment I would like from you is, India is planning for the sample return from Moon. So what should be our preparation for that? And how IIST can participate with the whatever labs which you see Umesh and others have.
Yeah.
So how we should prepare?
I would say for any sample return mission, curation is A and O. You were in Germany. You know what it means? No? A and O means, it is everything. Okay? It's curation is the most important, which also means it has to be rigorous. That means whatever we do have to be precisely maintained. The biggest thing is not to compromise the sample, its physical condition or other conditions. That's the first thing. And second thing is handling of the sample. So that would mean that not only we need extremely high clean rooms, that may be not a big deal, but also sample handling protocols that should be rigorous. And most likely, it would be good to have many labs that are needed clustered together.
Yeah, that is my concern because we may not get that opportunity here of extremely clean facilities. So how we can participate with the existing whatever instruments we have or spectroscopic capabilities what we have with the place where the samples will be
curated. So that one is much easier. Actually, what happens is, the NASA curated samples, the lunar samples, anyone can ask for samples. In fact, one of my collaborators from France got the Apollo samples to analyze the xenon isotopic ratio in that. It's Bernard Murthy from Nantes or some other place, not Nantes, some other place, okay. So we got that samples and we used them in our lab at JPL to do the spectroscopy. So the handling of that kind of samples is less rigorous because once you are given the sample, you are typically asked either are you returning it back, which means you need to be rigorous, or is it expendable sample? And if it is an expendable sample, then the rigorousness is less. But depending upon what kind of analysis you want to do, you still want to make sure that you're not contaminating and getting results that you think that they're great, which may not be great. Okay, That's why regressions is
So
important.
my opinion would be we should prepare in that direction.
Exactly. Yeah, anything even done here has
For
to
that,
be.
whatever protocol needs to be followed, maybe you can take some guidance from Murthy.
Yeah, I'll be happy to. Yeah.
Thank you.
Actually, in this context, one of the discussions which we were having with URSC is that from the lunar sample, because in Chandrayaan 4 that is a plan, the ice sample from the permanently shadowed crater of Moon. If we can get one sample here, of course, all these facilities we need to understand and understand the complexity of how to
Yeah,
maintain those
the problem is permanently shadowed craters on Moon. They are at 30 Kelvin.
Yeah.
30 Kelvin samples, if you want to get it out.
No, not in the cryogenic condition. We will have to get what we get.
So if it is a warm sample, then you need to be, it needs to be hermetically sealed as they get it in there. And when you get it here, you have to put it in, I would definitely say clean rooms. For example, if you're talking about isotopic ratio or rare gases, all those things. Even if it is not required, I would be more conservative and go one step ahead and get clean room where you put your instruments.
Some clean room.
Yeah. Yeah.
And also the load lock. And
load lock and
all those handling.
Yeah. All those things need to be there. Okay. Yeah.
Protocols are in place.
Yeah.
We have been handling UV instruments.
Yeah. So that's where I think that's what needs to be done. Yeah.
Okay. More? Not? Thank you very much.
Thank you.
For the nice talk.
Thank you.
Thank you all. There is some tea and snacks arrangement outside. You can have an informal discussion with the speaker as we take tea. Please join us.
Thank you.